Hello, my name is Shivdat. Today we're going to be looking at the Black Scholes equation, a really important equation in finance. Basically what it is and how to derive it. So the Black Scholes equation is a partial differential equation which is used extensively in finance, which governs the price of an option, a derivative that derives from some underlying over time. It was derived by Fisher Black and Scholes in 1973. And the idea from which they got it was to hedge an option perfectly in order to completely eliminate risk, which is called delta hedging. So without further ado, let's get started. Some of the assumptions made in deriving this Black Scholes equation are no arbitrage. In other words, it's not possible to make risk-free money on a risk-free investment. We're also going to assume that there is a risk-free interest rate R, in other words, an interest rate that you can use to borrow money, which is risk-free. We're also assuming that you can buy and sell fractions of a stock. In other words, you don't have to buy or sell stocks in whole numbers. You can buy 0.5, 0.3, 0.8 to 6 of a stock. It's infinitely divisible. And we're also going to assume that there are no transaction costs. In other words, we're dealing with a frictionless market. And so when you buy or sell a stock, you pay the amount that you're supposed to, and then there's no other cost involved for you or for the buyer if you're selling. And finally, we assume that the stock price follows geometric Brownian motion, which really means that the logarithm of the stock price follows Brownian motion. This is a very common assumption in finance, and it can be described by the following equation. If S is the stock price, then delta S of t to mu st dt plus sigma st dwt, where S of t is the stock price at time t. Mu is what's called the drift. Represents really a drift you can imagine in the Brownian motion, that random motion. Sigma represents the volatility, how volatile a stock is. In other words, the more volatile it is, the more its tendency to move much further away from its mean in either direction. Notice that these two are constants. The drift and the volatility are constants. And W is really really a parameter that basically you can imagine it moving up and down, satisfying the property that its average expected change over any time interval is 0. And its variance is t, but really imagine it as a quantity that varies such that its average change over any time interval is 0. That's what WG represents. So this is what geometric Brownian motion is. And these are going to be the assumptions made in deriving the Black Scholes equation. Alright, so now I'm actually going to erase these. If you've had a chance to internalize them, that's great. And I'm going to write down the Black Scholes equation on the top of the board. And then we'll get to deriving it. Right, so the Black Scholes equation basically is dv by dt plus half sigma squared s squared d2v by ds squared plus rs squared dv by dt minus r v equal to 0. So this is the grand Black Scholes equation that we're going to derive to. And what do all these quantities represent? Well, V is the price of the derivative, in most cases the option that derives from the underlying stock. Sigma is the volatility that we've already discussed. S is the stock price. And here you see V is the price of the derivative. R is the risk-free interest rate, S is the stock price, V is the price of the derivative, R is the risk-free interest rate. So that's it. The simple partial differential equation governs the price of an option, or more generally a derivative, a quantity that derives from a stock price, a financial asset that derives from a stock price over time. So now let's see how we go about deriving this. We had from the description of geometric Brownian motion that ds by s equal to mu dt plus sigma dw. This is nothing but geometric Brownian motion that I explained to you earlier. One of the assumptions was that the stock price follows this, right? So we label this as equation 1. Then we also have, now this is the one thing that I'm going to sort of pull out from a hat. It's called Ito's lemma. It's a result that describes what dV is in terms of a partial differential equation. Again, there's a derivation for this, but it's long, so I'm not going to get into it, but I'll try and give a justification of why it makes sense. So Ito's lemma for two variables, where V, the price of the derivative that depends on time, and the price of the underlying S, is equal to mu S dV by ds plus dV by dt plus half sigma squared s squared d2v by ds squared dt brackets plus sigma s dv by dt dv by ds dw. So this is Ito's lemma, and looks a little confusing. Comes from multivariable calculus, but the way to kind of make sense of this is that we're looking for the change in quantity of V. dV is a small change in V, the price of the derivative. And so what we really want to do is see how V varies on both its dependent quantities, time, and the underlying stock price, S, and try and get a formula from that. So V depends on S, we have that here. V depends on T, we have that here. V depends on S through the double derivative, the second order derivative. Again, V depends on S, and we want to use those quantities to multiply by certain factors to see how V depends on what a change in V can be represented as. So what we're trying to do is say dV equal to dV by ds times delta S plus dV by dt times delta T. And after that, there are all sorts of ways of rewriting this ds and this dt well, actually we don't rewrite this dt. If you notice dV by dt times dt, that cancels and you get left with dV. But this delta S can actually be represented by these terms, which is how we get Ito's lemma. We're not going to dive into that now, we're just going to leave it, take it as a given. Then, we also now assume that we have the following scenario. So let me rewrite these with letters. We also assume now we have the following scenario, that I've shorted one option. In other words, I've sold one option, one quantity, one stock of price S, and I've longed dV by d shares at time t. dV by ds shares, sorry, at time t. So in other words, short S and long dV by ds shares at t. Now the value of this portfolio, let's call it pi, is going to be minus V plus dV by ds, right, times S. Why is that true? The thing is, when you've longed something, you've bought it, right? So you really have this much times the number, you have these many shares, right? You've longed these dV by ds shares, and so what you really have is dV by ds times the price of a share. Well, you've also shorted, short one option V. So you've also shorted one option V, and so you really sold it, you don't have that quantity anymore, and so that gives a negative. So this is really what the profit is, and so delta pi is equal to minus delta v plus dv by ds times delta s. Right? So we're going to keep this as equation 3. And as you'll see later, we're going to equate two ways of calculating this profit, of writing out this profit, and that's what will ultimately lead us to the Black Scholes equation. Now also notice from this geometric Brownian motion, if I rewrite the derivative d in terms of delta, I could really say delta s, right, is equal to, and this was s here, is equal to mu s delta t. Mu s delta t. So I'm multiplying that s across, and I'm replacing dt by delta t. Similarly, dw by delta w, and I multiply that s across. So delta s equal to mu s delta t plus sigma s delta w. Let's rewrite it this way in terms of delta, since we're dealing in terms of deltas, it'll make it easier and it'll make things cancel. Now, notice that if I were to put also, let's see, so I want to basically put the value of delta s into this equation I've just written for this, into the expression for delta pi, the change in portfolio. So I want to use this in here. But I also know that, again, in our way of writing d as delta v, so dt I'm going to write delta t, and dw I'm going to write delta w. Now notice, if I put these two equations, equations 1 and 2, into equation 3 for delta pi. Now I can do this on the board, but it'll get messy, so let's try and do it in our head. It's actually not that hard. So delta pi equal to negative of this plus dv by ds times delta s. dv by ds times delta s. So let's multiply this by dv by ds. dv by ds, dv by ds, dv by ds, and we have all negative signs on here. So notice that what's really going to be left are these two terms. And why is that? Mu s dv by ds delta t. But we also have mu s dv by ds delta t with a negative sign in there, right? Because this has a negative sign from delta v, and that has a positive sign. So this is going to cancel with this when you multiply it by that delta t. Similarly, also have sigma s dv by ds delta w. We have sigma s dv by ds delta w, right? Which is exactly the same. So this will cancel with this. Notice you have opposite signs from this negative v, negative delta v. So all you're really left with is delta pi equal to this, equal to minus negative v, so minus dv by dt minus half sigma squared s squared d2v by ds squared times delta t, right? And let's keep this as equation 4. Good. Now we come to an important point. Basically, also notice that the delta W has vanished from this equation. In other words, it's become riskless. The portfolio is riskless now after this hedging has been done. But notice that the rate of return, R, then should also be equal to the rate on any other riskless instrument. Because if it weren't, there'd be a possibility for arbitrage, there'd be a possibility to make risk-free money. In other words, whether we invest our money here or in any other risk-free instrument, we should really get the same, we should have the same rate of return, it shouldn't be different. Or in other words, what it's saying is that if I have profit, if my portfolio is worth pi, and I keep for time delta t, right, and my rate of return is r, then delta pi should also equal to pi times the rate of return times delta t, which is equation 5. So what I'm going to do now is just equate these two equations for delta pi, the change in the value of the portfolio. And we used A, B, and C to really get to this first expression for delta pi. We used a logical argument to get to the second expression. So I'm going to erase A, B, and C right now. So in other words, if we equate this and this, what we get is minus dv by dt minus half sigma squared s squared d2v by ds squared delta t r pi delta t. Right? And now we can rearrange this to say, let's take dv by dt that side, so dv by dt, let's take everything that side, right? Plus half sigma squared s squared d 2v by ds squared. Notice the delta t's are going to cancel, right? And we also know that pi was minus v plus dv by ds. How do we get that? Remember, pi is the value of our holdings, which is minus v because we've shorted one option, plus dv by ds, that's how much we're selling of stocks. That's how much we're buying of stocks, right? So we want to say plus r pi minus r times v plus r pi, r times r dv by ds into s is equal to 0. And what is this? This is nothing but the Black Scholes equation that we have on top. dv by dt is half sigma squared s squared d2v by ds squared minus rv, note the order of the terms were interchanged, plus r s squared. Oh, and there's an s here as well. S squared. Oh, sorry, no. Yeah, sorry, that there shouldn't have been an s squared there. So that's really how you derive the Black Scholes equation. Yeah, my apologies, I shouldn't have written this. It's just a simple s for the Black Scholes equation. So really, that's the idea behind writing this partial differential equation that governs the price of an option at any time. Now it's another matter to solve this. It's tricky. They have solutions, but you know, they're not very straight. It's not a simple matter to solve this equation. But just to recap, basically, we derive this equation by finding two ways of looking at delta pi, the change in the value of portfolio. One was common sense by saying delta pi is value of the portfolio times the time, delta t, times the risk-free interest rate. Since the risk-free interest rate on any other holding should be the same. And the other way we calculated it was by combining, was by knowing that delta pi is minus delta v plus dv by ds times delta s. In other words, you've shorted one option and long dv by ds shares. So that's the value of the portfolio. And into that expression, we substituted the value of delta s, which we got from geometric Brownian motion. And we also substituted the value of delta v, that we got from Ito's lemma to come up with an expression for delta pi. We combined those two values, those two expressions of delta pi, equated delta pi, yes, the value, change in the value of the portfolio, equated them, and our result is the Black Scholes equation, one of perhaps the most famous equation in finance today. Thank you.